Hello everyone, I'm Dr. Nandy. Welcome to my YouTube channel Ecstasy of Physics. I have come with another video of APPhysics 1 series. In this video, we'll be talking about the review of energy. To review the energy, we'll be talking about the work, power and energy. Since work consists of force, displacement and angles, we'll be going to in details about depending on the different angles. We'll be having the positive, negative and zero work done. Force will be defining the force in terms of conservative and non-conservative force. Then after that, we'll be defining this energy, conservations of mechanical energy, classifications of energy, work energy theorem and its applications. After that, in APPhysics 1 we have mainly the mechanical energy, which consists of the kinetic energy and potential energy. Then the potential energy we are going to define in terms of gravitational potential energy, elastic potential energy and electrical potential energy. This is the interference structures of energy in under APPhysics 1. To define the work, we can say work is the product of force times displacement. That's representing the work done. So it's the force times displacement. Let's say one object is located here. The mass of the object is m. On the object we are going to apply the F amount of force, and due to the force applied, the object it got displaced by a certain distance. Let's say s is representing the amount of displacement. Now to define the work done, we can say W, that is equal to F dot S, where this force and the displacement both are representing the vector quantities. Here we are doing the dot product or scalar product between them. So whenever we will be going to write on the magnitude, so that will be giving that F into S into cosine theta, where this theta it represents the angle in between force and displacement. So finally the expressions of work done we are getting, that is F into S into cosine theta. Now this work done it is a scalar quantity. The meaning of that, it will be only having the magnitude but no directions it is having. The unit of work done, SI, unit of work done, that is joules. And depending on this value of theta, the work done we can classify into like different way. In the sense, we can define the sign of work done. The work done, it could be positive, it could be negative, as well as it could be zero also, and all basically depending on the value of theta. The classifications that we can do depending on the value of theta. So first of all, the positive work done. To define the positive work done, we can say, let's consider one object is located here. On the object we are applying certain amount of force along these directions, and the object got displaced along the horizontal directions. This is the directions of displacement, and theta, that represents the angle in between force and displacement. So here you can see the theta, the angle it has to lie in between 0 to 90 degree, or you can say in between 0 to 90 degree, where it could be 0 as well. So in that case, the work done, it would be the positive work done, because in this range, in between 0 to 90 degree, in this range, the cos theta, it would be positive. Cos theta, it would be positive. And then in that case, the W, what will be getting, that will be equal to positive work done. To get the negative work done,
The negative work done, it can be defined as let's say one object, it is in moving condition, and we know that always the frictional force it exerts in the opposite directions of its motion. So this force is representing the frictional force which is exerted on the object by the surface, and the object is moving in the positive x-axis direction. So in that case, the directions of force, it's in the opposite directions of its motions. And now if we have to define the work done due to friction, this work done due to frictions, that will be representing the to define that work done due to frictions, we can say that ff times by s into cosine of theta, where this theta at present it is equivalent to, it is equal to 180 degree, which means the range of theta, if it is in between 90 to 180 degree. So in that case, that cosine 180 degree or cosine theta, that would be negative, because the cosine theta it comes in the second quadrant, and the second quadrant cos theta is negative. So from there we'll be saying that here the work done, it would be negative. Next we are having the zero work done. To define the zero work done, we can say, let's say the one object which is placed on the ground, the gravitational force exerted on the object in downward directions, and the surface is offering the normal reactions force on the object, that is Fn, and let's say due to the force applied, the object got displaced along the horizontal directions. Suppose if I am to define the force, the work done produced on the object due to the normal reactions, then to define that work done produced on the object due to normal reaction, in that case we'll be considering that Fn times by s into cosine of theta, where this theta at present it is the angle in between the normal reactions force and the angle directions of displacement. Presently this theta it is 90 degree, and cosine of 90 degree, that is equal to 0, which means from here directly we can say the work done due to normal reaction force, it would be 0. So basically these are the three types of classifications depending on the value of theta. We can say positive work done, negative work done, or zero work done. Next we are going to talk about the graphical representations of the work done. Graphical representation. We have defined already the work done is the product of force and displacement. So let's draw the graph by plotting the force. It is exerted along the, or it is shown along the y-axis, and the displacement it is along the x-axis. Now on any object, if any constant force is applied, constant force means the magnitude of the force, it should be uniform. So in that case it can be represented in the graph by this line. So that will be representing the constant force is acted on the object. Now due to this constant force exerted, what should be the work done? So in that case, suppose if I am to find out that in between the 2 points, when the displacement from the point A to the displacements to the point B, what would be the work done? So to define the work done, we have to find out the area under the curve. Area under the curve, that represents the work done. So here specifically we can say area under the curve of force displacement graph, that represents the work done. So at present the work area under the curve, that would be force times displacement. Displacement is from the A to B, that means B minus A. So that would be representing the total area under the curve, and which is representing the work done. And this can be represented by this highlighted section. To define the work done, we have defined that force times displacement. Now this force also we can classify into two ways. One is that conservative force, and the next one is the non-conservative force. Non-conservative force. So to define the conservative force, let's say one object which has started its motions from any point P, by keeping that, by considering O as the center, and it is following a circular path. After a complete circle, it has reached to its original positions, means it comes back to the original position again. So in that case, what would be the total displacement? The total displacement, it would be 0, since the initial and the final position are represented by the point P. Starting and the ending positions, it is represented by the point P. So here in this case of the total displacement is 0. Now to define the work done, it would be like force into displacement, F into S. Since the displacement is 0, we can say that however the force is exerted on the system, but this work done, it becomes 0 here. So here that means in case of conservative force, we can define if work done by a force during a round trip of a system, if it is 0, then the force is known as a conservative force. So in case of the conservative force, the work done, it would be 0 for a round trip of the motion. And the example of the conservative force that you can consider as like gravitational force. Gravitational force, or you can say the magnetic force, electrostatic force, then magnetic force, all are representing the conservative forces. What about the non-conservative force? That means non-conservative force, it would be the opposite of that, which means it can be stated that the work done, it should not be 0. Work done, it should not be 0 for a round trip of the motions. Then how it can be properly justified? So for example, whenever the object is moving on the ground, there would be a frictional force in between the object surface and the ground, and that frictional force is causes a certain amount of it produces certain amount of heat, right? Because we know that whenever there will be a frictions in between the object surface and the ground, there will be a heat is produced, and that heat basically we can consider is the work done due to frictions. That is not going to be remaining in the system, it is dissipated from the systems during its motion. So work done due to frictions, that we can define as frictional force times by the displacement, and that work done, it will be also counted. And whenever there will be what are the forces will be responsible that to produce this type of work done, however the total displacement is 0, but this frictional force will be responsible to do certain amount of work done, and that those forces are known as the non-conservative force, and that can be defined specifically that work done must not be 0 for a round trip. The examples of non-conservative forces are the frictional force, viscous force, air drag force, which means any kind of resistive force will be representing the non-conservative forces. Next we'll be talking about power. To define the power, we can say the rate of work done by a body, that will be representing the power. So mathematically the power, it can be expressed as its work done by an object or on the object per unit of time. So that's representing the power. which is basically representing the rate of doing work. So the work done earlier we have defined that force times displacement. So it's F dot S. This is a vectorial form of representations upon time t that can be represented by that is representing the power. So it's F dot S upon t. S represents the displacement, and we know that displacement per unit of time that representing the force. So that means F dot V. This is the vectorial form of representations of the power. This is also the vector, or you can say the dot product in between force and velocity that represents the power. From here, if you want to write the magnitude, then you will be writing as F into V into cosine of theta. So that's representing the power. Now how it can be expressed means by the diagram. On any object, if you are going to provide certain amount of force and due to which the object is moving with certain velocity and the angle is formed in between the directions of velocity and the force applied, so in that case the power, it can be defined by this formula, that P equal to F into V into cosine of theta, where theta it represents the angle in between the directions of force applied and the directions of velocity. The power, it's a scalar quantity. Like work done, the power is also a scalar quantity, which means it will be only having the magnitude but no direction. And what would be the unit of power? The SI unit of power that can be represented by its joules per unit of time. So joules per second, and that is known as the watt. In short, it is represented by W. There is other form of power also, means there is other form of unit is also having. So that is, we can define as horsepower. And the conversions of horsepower up into watt, that we are considering as 1 horsepower, that is equal to 746 watt. The horsepower, in short, it is represented by HP. Now we are going to talk about the main content, which is energy. To define the energy, we can say the energy of a body is its capacity of doing work. So it's basically the capacity of doing work that is representing the energy. Similarly, work done, the energy is also the scalar quantity, and the unit of energy, it can be defined by SI unit of energy, it can be defined by joules. And there is one more unit of energy we are using mostly, that's called the kilowatt hour, 1 kWh. So the full form of this, 1 kilowatt hour. So 1 kilowatt, it can be written as 10 to the power of 3 watt, and 1 hour, that can be written as it's 3600 seconds. Now this watt, it can be represented as its joules per second times by its 3600 seconds. So from here, this second and second is eliminated, we'll be getting that it is 3.6 into 10 to the power of 6 joules, which means it's 3.6 megajoules. That's the representations of the 1 kilowatt hour. So this kilowatt hour is a unit of energy. Next, we are going to talk about the classifications of energy. Classification of energy. The energy, it can be classified into several ways. For example, the mechanical energy, then chemical energy, then electrical energy, nuclear energy, thermal energy, then renewable energy. So there will be like many different ways the energy can be classified. Again, this renewable energy also, it can be classified as solar energy, then wind energy, tidal energy, geothermal energy. However, we don't we have to just go through the basic ideas of the different types of conversions, but in AP Physics 1 they are not going to ask like so many details and all. So mostly what we have in our sections, that is the mechanical energy. That's the vital one, and we have to analyze that mechanical energy properly. The mechanical energy, it can be classified into two ways: kinetic energy and potential energy. And this potential energy also, it can be classified into different types of potential energy we have. For example, the gravitational potential energy, spring potential energy, which is very important concept from mechanics point of view in physics, then electrical potential energy, however this electrical potential energy, it's a main part of AP Physics 2, but slightly we have in our sections, that is the electrostatics, under which will be small discussions we'll be having on electrical potential energy as well. So first of all, the kinetic energy. Kinetic energy which is related to the motion, or specifically we can say the energy possessed by any object by virtue of its motion, that will be considering as the kinetic energy. So we can say the energy possessed by any object due to its motion. So that's representing the kinetic energy. The expressions of kinetic energy, mathematical expressions of kinetic energy, it can be represented as half m v square, where m stands for mass of the object and v stands for velocity of the object, which means if the object it is in rest condition, the kinetic energy it would be 0, and it can be expressed as EK. That's the form of representations of kinetic energy. Since the kinetic energy is a part of energy, and earlier we have defined the energy is a scalar quantity, so here also we are saying that kinetic energy is also a scalar quantity and its SI unit same as energy, that is joules. Then there will be relations we have to establish in between the kinetic energy and the momentum. Kinetic energy and the momentum relationship. This relation, it is quite useful because most of the time we can quickly switch from one form, means one energy equations, to the momentum form. So energy we have defined EK, that is equal to kinetic energy equal to half into m into v square. Now in these expressions, if you multiply m in with numerator and denominator, means it is a adjustment I am doing, So finally we will be getting that half into m square v square upon m, and from there this mv square means m square v square can be written as is mv square by m. And according to the definitions of the momentum is the product of mass times velocity, and it is can be represented by p. So from there we can say mv, that is substituted by p square, that p stands for momentum, upon m. So this is the relations in between momentum and the kinetic energy, or it can be represented as p square equal to twice into m into ek, which means that p equal to square root of twice into m into ek. So any of the conversions we have to remember. Next we will be talking about the potential energy. The potential energy, it can be represented for an object due to its shape, size or configuration, which means we can define that the energy possessed by an object by virtue of which or we can say by virtue of its motion, of its positions, shape or configuration. So that's representing the potential energy. Earlier we have defined the classifications of potential energy. So under the potential energy, first we are going to talk about the gravitational potential energy. Gravitational potential energy. To define the gravitational potential energy, let's consider an example. If an object whose mass is m, initially it was placed on the ground, and we need to shift this mass on the top of a, let's say, building whose height is represented as h. Then in that case we have to do certain amount of work done. Now the force, the gravitational force exerted on the object, that will be Fg downward, and the displacement, it is in the upward. So now to define the work done, the amount of work done which has to be done on the object, that can be represented as is the gravitational force times by displacement Fg times s. Now the gravitational force is exerts in the downward directions into s into cosine of theta. Gravitational force, it can be represented by is mass times gravity, so Fg can be represented by mg. Displacement, it can be represented by h, where h is representing the height of the section on which the object has to be placed. So times by, instead of s I am writing h. And what about theta? So presently this theta, it is 180 degree. So that will be representing the work done. And from there cosine 180 degree, that is equal to -1. So finally we are getting the expressions of work done, that is negative of mgh. And finally we can say the change in potential energy or change in gravitational potential energy. Gravitational potential energy in short, and we can write it down as EP. So change in gravitational potential energy, that is negative of work done. Why it is negative? Because we are doing certain amount of work done, and it is going to be stored in the object in the form of gravitational energy, due to which since the work done on any object is considered as negative, so here we are saying that it's a negative of work done will be representing the change in gravitational potential energy, and the work done expressions that we have got negative of mgh. If you substitute in these expressions, finally you are getting the expressions of potential energy, which is equal to m into g into h. That's the expressions of the gravitational potential energy. Next we'll be going to talk about the elastic potential energy. Elastic potential energy. The elastic potential energy, to define that, we can consider an example. Let's say one object, let's say one spring with which a mass m is attached. Initially it is in equilibrium condition. That means there is no displacement of the spring. That means it can be considered as x equal to 0, which is representing the equilibrium condition. Now once we are applying certain amount of force, the spring, it got elongated and it has displaced to some new position. Let's say x, it got displaced to some new position. It's a elongated condition. Whenever we'll be removing that external force, the object will come back to its initial positions, and not only come back to its initial position, it will be start compressing. So definitely there would be a factor responsible for that, and that factor is known as the restoring force in the spring. The restoring force, it can be represented here, that is Fr, which is proportional to the negative of displacement, because the displacement is happen in the positive x-axis directions, but due to the restoring force, the object will come back to its main position, due to which we are considering that restoring force is exerted in the opposite directions of its displacement, and it is proportional to the magnitude of displacement. If we are increasing the magnitude of displacement, that means if the spring is more stretched, then in that case the restoring force built inside the spring, that will be also more. So from there we can say the restoring force, that is equal to negative of k into x, where this k is representing the spring constant. Spring constant, this will be also represented as the force constant, or in different book it could be represented as spring stiffness. Spring stiffness. Now to find out the amount of energy is getting stored in the spring during this restoring force, or due to the restoring force the amount of work is being done on the spring, so due to which how much potential energy is going to be stored, that we are trying to find out. So let's find out that amount of work done. The amount of work done, it would be, we can represent here, that's the average force times by the displacement. The expressions of the average force, we can say, when the displacement is 0, the restoring force is 0. When the displacement is x, the restoring force is represented by Fr, that is equal to negative kx. That means we can take the mean of these forces, so it would be 0 plus Fr upon 2. That's representing the average force times by how much it got displaced. The displaced is the x. So it is basically half into restoring force Fr times by s. Now the restoring force, it can be represented by this expression, negative k into x times by x. And finally we are getting the expressions of work done, that is negative half into k into x squared. Now the thing is, the amount of work is been done on the spring, that is going to be stored in the spring in terms of spring potential energy. Spring potential energy. So the spring potential energy expressions, it would be negative of work done. So spring potential energy ES, that can be represented as negative of negative half k x squared. And finally we are getting the expressions of spring potential energy ES equal to half k x squared. That's the expressions of spring potential energy. Next we'll be talking about the conservations of mechanical energy. Conservation of mechanical energy. We have earlier defined that mechanical energy, it's a combination of potentials energy and the kinetic energy. Now according to the conservations of mechanical energy, the summations of kinetic and potential energy at any point, it will be remain constant throughout the motion. So that's representing the conservations of mechanical energy. So it doesn't depend upon time and it is independent of its position. So total energy magnitude, it will be always conserved. We can say the total mechanical energy is always constant at any point irrespective of the time. And that can be represented as the mechanical energy, total mechanical energy E, or you can say TE, that will be the summation of kinetic energy and potential energy. Now this potential energy, it could be different types of potential energy. It could be like spring potential energy, or it could be like gravitational potential energy. So presently let's consider the kinetic energy is half mv square and the gravitational potential energy is mgh. And that situation you can consider as let's say one ball which has been dropped from a certain height h. Initially the velocity of the ball, it was 0, and after that it is being dropped from the height h and it is going to strike the ground with a particular velocity v. So from the motions from the point A to the point B, during its path always will be considering that energy is conserved. However, we are going to neglect the air resistance or air drag. We are not going to consider here. So which means if in between like any positions will be getting, like if this positions is represented by C, so at the C point also the energy, if we compute, then the summations of all the summations of energies at any point, total energy at any point, it will be conserved. For example, at the point A, it will be only having the potential energy, gravitational potential energy, since the velocity is 0, which means the gravitational potential energy expression, that is mgh here. If at the point B, here it will be only having the kinetic energy, and expressions of kinetic energy is half mv square h equal to 0, due to which the potential energy, that will be 0 at the ground. Now we can, according to our consideration, the total energy, it will be conserved, which means the total energy at the point A, that is equal to the total energy at the point B. And by considering that, we can make a relations in between the velocity and the height. Total energy at the point A, that would be m into g into h, and total energy at the point B, which is equal to half into m into v square. Now this m and m is eliminated and we are getting v equal to square root of 2gh. So by the help of the total energy conservation, we can easily determine that what would be the velocity if it is fallen from a certain height. And from these expressions we can say the final velocity, it only depends on the height. It is independent of the mass. Similarly we can consider, let's say there is a frictionless track and one spring is attached, or you can say one spring, it is represented here. One end of the spring, it is fixed with the one surface and other end it is free. Now one object which is moving with a particular velocity v, since I have mentioned that it is a frictionless track, so mu equal to 0, that means the same velocity it is going to be maintained, and the mass of the object is m. After, due to the force exerted due to the motions of this block, what could be the possible or what could be the maximum compressions that we have to find out. If the spring constant of the K, if the spring constant that can be represented by K. So now here also we are going to apply the conservation of energy to get this means to solve this problem. So here the block is moving with a particular velocity, that means the block is having the kinetic energy that can be represented by half into m into v squared. Since after compression the end of the spring it will be shifted here, and that will be the maximum compressed condition, and at this position the velocity it becomes 0, which means at this point if you want to find out the spring potential energy, that would be half into k into x squared, but the kinetic energy of the system it becomes 0 since the velocity equal to 0. And at the initial position when the spring it was in free length condition, there is no compression, in that case we will be considering the spring potential energy that is equal to 0. So if we make a comparison in between the point 1 and the point 2, so in between point 1 and 2 we can say the total energy is conserved. So total energy at the point 1 that is equal to the total energy at the point 2. Total energy at the point 1 it would be the summation of kinetic and spring potential energy. Similarly at the point 2 also the total energy it's the summation of kinetic and spring potential energy. Kinetic energy at the point 1 it would be represented by half mv squared, since the spring potential energy at the point 1 is 0 and kinetic energy at the point 2 is 0, and spring potential energy it would be represented by half k x squared. Now easily we can make a relations from here that m v squared and that is equal to k x squared. You can determine anything like what would be the initial velocity of the block. If we have the x value, then from there we can say the v equal to its k upon m square root of that times by x. So this is a very useful equations in our calculations part. Now in case of by applying the conservation of energy, we can make a very interesting numerical on simple on you can say that a pendulum motions. So let's consider one object is located here, means it is a pendulum is located here, it is the mean position, and here the pendulum it got shifted to its extreme positions by making an angle theta. This position is considered as the extreme positions of the pendulum, and we can consider this is the reference position where the h is equal to 0, and from here the pendulum how much it got shifted, that is equal to h. And once it will be comes back to the opposite end, so that will be represented, so a and b, those are the two extreme positions of the pendulum, and c is representing the it is a mean position, mean positions or equilibrium positions of the pendulum. Mean or equilibrium positions, here we are considering that x equal to 0, and a and b are considered as the two extreme positions. At the two extreme position we are always considering that velocity it is equal to 0, v equal to 0 at b and a. Since the velocity equal to 0, we'll be saying that kinetic energy it is equal to 0. And at the point c, as it is the h equal to 0, so that means at the mean position we'll be considering that potential energy it is equal to 0. So now here also we can apply the conservation of energy in between the point a and c. The total energy at the point a that is equal to total energy at the point c. Total energy at the point a that we can write in terms of mg into h. H is representing how much vertically the bob is shifted, and m is representing the mass of the bob. Total energy at the point c that is half into m into v, and here basically that velocity of the bob it will be in both the directions during its motions, during its oscillations, and that velocity it is basically considered as the maximum velocity. So from there, after solving that, you will be getting the expressions of the maximum velocity. It is square root of twice into g into h. That's the maximum velocity here. And the next one we'll be talking about in energy part, we are having a theorem that's known as the work energy theorem. According to work energy theorem, we can say the amount of work done on any object, it is equivalent to the change in kinetic energy of the object. For example, let's say this is an object whose mass is m, which is moving with certain velocity u. Once the force we have applied on the object, and due to the force applied, the velocity of the object, it got changed, and its final velocity represented by v. Since we have applied the force, and due to which certain amount of work is being done on the object. Now according to this work energy theorem, the work done on the object, that is represented up by W, and that is equal to change in kinetic energy. Change in kinetic energy that can be represented by is the final kinetic energy minus initial kinetic energy. Final kinetic energy, that will be representing the final position here, and this is the initial position here. According to the final kinetic energy, we can say it's half m. Since the velocity at the final location is v, so the final kinetic energy, it becomes half m v square and half m u square. Since the initial locations, the velocity is represented by u. So the expressions of final kinetic energy and initial kinetic energy is half m v square minus half m u square, and that is equal to work done W. This is known as the work energy theorem. Now this work energy theorem, it includes the non-conservative force as well, which means during the, here I did not consider the friction, mu equal to 0. In that case, if there will be a frictions offered by the surface, so we have to consider the frictional energy loss as well. So we have to take care in the equations the frictional energy loss, and that will be also included in work energy theorem.